Okay folks, welcome to the next video. In this video we're going to take a look at using differentiation to locate turning points. So turning points have lots of different names. They're often called, I'll generally be calling them the turning points, but they're often called critical points, stationary points, or in the more formal kind of mathematical language, the maxima and minima of functions. They're essentially the highest point on a curve or the lowest point on the curve. How do we find these points here? So if we take a look at some of the functions we've already encountered, we have the linear function. This is just a typical example. Y is 2x plus 3. We look at the graph and there's no turning point. The slope is always positive. In this case it's got a slope of 2. We've got our y-intercept, but there's nowhere the curve continues at this slope for infinity. So it never turns. So a linear function has no turning points. Remember, we identify a linear function, highest power on x is 1. Quadratic function, say y is equal to x squared plus 2x plus 3. A quadratic function has one turning point. It's either a minimum point if x squared is positive. Remember, positive x squared gives us a smiley curve. So then this is the turning point when it stops, the slope stops being negative and starts being positive. Or we can have a maximum point if the x squared value is negative. So if there was a minus in front of the x squared, then we get a not smiley curve, which looks like this. And the turning point there is a maximum point. So we can identify the type of turning point we have with a quadratic by looking at the x squared value. Is it positive or negative? We have a cubic function. This is a polynomial. Polynomial just means many numbers. So there's more than one x term. If we've only got an x cubed term, we'll see that on the next slide. It's a simple cubic. This is a polynomial. And a polynomial cubic has two turning points. One maximum and one minimum. So this is what we're typically looking at. There's the max point and there's the minimum point. These are often called a local max. Just sometimes you'll see that. And a local min. You'll see that often written in textbooks. Then we have a simple cubic function. This is where we just simply have an x cubed term. Now it might have a constant as well, but there's only one x term. And obviously that has to be cubed in order for it to be a cubic function. These are the type of ones we would encounter most commonly in science. And this has one stationary point. It is a turning point. And this is often called a point of inflection. And this is it here. So it's like where a local max and a local minimum point meet at the same place. And that's called a point of inflection. So they're the typical turning points that we'll be examining: local maximums, minimums, and points of inflection. Now, how do we find a turning point? So at a critical point, the slope of the tangent to the curve is 0. So this is our mathematical basis for finding these points. So essentially, at these critical points, stationary points, turning points, maximum, minimum, whatever you want to call them, the crucial thing is at this very moment, the function value has stopped going down, the slope has stopped being negative. It hasn't started being positive yet, so this is where it's at the exact moment where the slope is 0. That's what happens at a turning point. So dy dx is 0 at the turning point. So we're just going to take a look at locating where the turning point is, and then later we'll look at how do we identify the nature. Is it a max? Is it a min? Is it a point of inflection? So determine the critical point of this function, y is equal to x squared plus 2x plus 3, and state its nature. Well, what do we know about this curve? Well, it's got a positive x squared, so it's smiley. And that's what we're looking for. We want to identify the lowest point that the curve reaches. That's our goal with finding the turning points. And ideally we want to do it without drawing a graph, because as we've already learned, drawing graphs can be quite tedious, and there can also be the potential for significant error depending on the level of accuracy that we're looking for. So just to kind of give you a quick visual picture of what we're trying to do. Imagine you've got a bicycle and you've attached a spirit level to the crossbar of your bike. So here's your bike, and we're tying a spirit level to the crossbar there. Now, as we kind of cycle up and down the hill, so if we imagine the curve is actually a series of hills and valleys, the only place where the bubble will be exactly centered is either at the very peak of a hill or at the very lowest point of a valley, or at a point of inflection, if that's what we're looking at. So that's what we're looking for. We're looking for this idea of where is the slope equal to 0. And we're trying to center the bubble. At what moment is the bubble exactly in the center of the spirit level? And at that point, where the slope is 0, that's where our turning point lives. So this is the mathematical basis then of what we're going to be doing. We're trying to find where the slope of the function is 0. So for a minimum curve where x squared is positive, that's what we're looking for. For a max of a quadratic. So all the time we're looking for where is the spirit level, so to speak. In a point of inflection, that's where it occurs. So this is the basis now of how we're going to go about our work. We want to find where is the slope equal to 0. So just a quick step-by-step, how do we do it? Well, first thing we want to find the slope function dy dx. Remember, that's all dy dx is. It's a function that gives us the slope at any value x on the curve. We want to know where is the slope 0. So once we've found dy dx, we then let dy dx equal to 0. It just becomes an equation. And we solve for x. If we're looking at quadratics, we'll only get one value for x. But sometimes with cubics, there'll be 2 x values. Once we know our x values, we substitute each value back into the original function you were given with the question. So once we find x, we want to find y. And if we take a look, what function gives us y? This function, the original function, tells us what y is. So we substitute in the x value and solve out, and then we'll be able to find y. Remember, a, b, and c are just constants. So later on then, we'll take a look at how we determine the nature of each point. But at the moment, we're just going to do it kind of intuitively. But we need something a bit more kind of mathematically solid than just intuition to do these properly. So we take a look. We've seen this example. So determine the critical point of y is equal to x squared plus 2x plus 3 and state its nature. First, differentiate the function, find dy dx. So this is the original function. When we differentiate it, dy dx, I'll just change the color. We'll just do it I'll just do a quick re-step. So remember dy dx, we just do each term separately. When we differentiate this, the 2 comes down, we reduce the power by 1. When we differentiate 2x, we just get plus 2, and that's our derivative. Now we're interested in, well, this is the slope function. This will give us the slope for any value of x. We can just feed in x into this, any value of x, and it'll give us the slope at that point. But we're interested in, where is dy dx 0? So we want to make dy dx equal to 0. So we're really interested in just letting this equation equal to 0. And now we solve for x. Bring the 2 over. Divide both sides by 2. And x is equal to minus 1. So what this tells us, guys, is somewhere along this line where x is equal to minus 1, somewhere along this line our turning point is going to be. But we don't know exactly where yet, but we know it's somewhere where x is equal to 1. We want to find the y location. What's the y coordinate? So to find the y coordinate, we substitute our x value back into the original function because it tells us y is equal to. So now we know on the x-axis where the turning point is, at minus 1. To find the y value, we substitute this x value into the original equation. And then get your calculator or work it out in your head, preferably. We get y is equal to 2. So now we know our turning point occurs at minus 1, 2. Our function has a positive x squared, so that means it's a smiley curve. So in that case, our turning point must be a minimum point. So this is what I mean by the intuitive analysis, by what we know about quadratics, smiley or not smiley. That determines whether we're dealing with a maximum, or in this case, a minimum point. Positive x squared for a quadratic will always give us a minimum point because of the smiley nature of the curve. Now we do the same. It's a different curve, but now notice the x squared term is negative, which gives us a not smiley curve. So that means when we find this point, we know it must be a maximum point. First step, find dy dx. And now we're going to we're interested in, well, where is dy dx equal to 0? How do we find this point? We find it where the slope is 0. And m, guys, remember, is dy dx. Dy dx is equal to 0. So we're going to let this equal to 0. Hop the 4x over to the other side. And then divide both sides by 4. And we now know that our minimum point occurs somewhere along this line here. But we don't know where. Could be anywhere. So we need to kind of feed this x value now back into our original function. Don't feed it in here, guys, because you're going to end up with 0. We've already, you're guaranteed to get 0 if you feed it into the red equation. But we want to find the y value, and that's what that function gives us. So add x is equal to 4. Feed 4 into the x parts for here. Get your calculator or not, and we'll end up with y is equal to 36. So now we've identified our turning point. It occurs at 436. Because my x squared term is negative, sorry, I should include the minus sign, then I know it's a not smiley curve. So my turning point then is a maximum point. So the negative x squared with a quadratic ensures we're dealing with a maximum point. Another one. This one looks a little bit trickier. Determine the turning points of the following function. Well, first thing we're going to do is multiply out the brackets using FOIL. X by x gives us x squared. Outer, x by minus 5 minus 5x. Inner, minus 3x. And the last terms gives us plus 15. So this will now give us x squared minus 8x plus 15. This function is a lot easier to deal with. Now, if you wanted, guys, you could actually go and use the product rule. If you remember from the previous lecture, we have two terms and we could say this is u and this is v, but it's a little bit long-winded. It would certainly get you there, but it's much quicker just to multiply out the brackets and then find dy dx. The 2 comes down, we reduce the power by 1, and there's our derivative. Now we're interested in where is this function equal to 0, because this is the slope function, remember? That tells us the slope at any point on our curve. We want to know for what x value is dy dx equal to 0. Bounce the 8 over to the other side. Divide both sides by 2. And we've now located where on the x-axis the turning point occurs. It's a smiley curve, so it's going to look something like this. But again, we don't know the y-coordinate. We just know in terms of x that the turning point is going to be somewhere along this dotted line. So to find our y value, we feed this back into our original function and solve out carefully. Be careful here, guys. It's often at this stage people make the mistakes. Actually, it's very often at this stage people just not paying attention. So it's plus 31 when we add together the positive values, minus 32, y will be minus 1. It's a smiley curve. Our turning point now we figured is at 4 minus 1. Because it's smiley, our turning point must be a minimum point. So a positive x squared gives us a minimum point. There's just a quick picture of the graph. So now here's some questions for you guys to have a go. Just pause the video. I want you to find turning points of the following functions and then state whether they're a maximum or minimum point based on the sign on the x squared value. So have a go with each of those. And we'll just push on then with the rest of the lecture. So now we're going to take a look at determining the stationary points of a cubic function. It's the exact same process. We want to find dy dx first of all. I'll just go through that again. So for our first term, bring down the power and add minus 1 to the old power. Same for the second one, we'll have 6. The constant stays, bring down the power, add minus 1 to the old power. plus here, when we differentiate 9x, the x just gets knocked out. We just get the constant remains. And when we differentiate a constant value, remember that just goes to 0. So our derivative is 3x squared. Here numbers do what numbers do. 6 by 2 is 12, so minus 12x plus 9. So I just write that out a bit neater. And now we're interested in, well, where is this equal to 0? So we've got 3x squared minus 12x plus 9 is equal to 0. And we actually have to factorize our equation. So what I would do here, because it's equal to 0, we could divide across by 3. And then we'll factorize. I won't spend ages on it. X minus 1 and x minus 3. Quick check, that's okay. And there's our factors. Now we let each bracket equal to 0. This will give us x is equal to 1. We let the other bracket equal to 0. Bring the 3 across, we get x is equal to 3. So now we've identified we're dealing with a polynomial cubic, so we're expecting 2 turning points. So what we found out is that, well, one turning point happens when x is equal to 1, and the other turning point happens when x is equal to 3. But we don't know anything else. It could look like this. It could be a maximum here and a minimum there. Or it could be a minimum and then a maximum. So we don't really know. There's an infinite number of possible arrangements that we could have max and minimum points occurring at these 2 locations. So we need to find the y value, but we know what to do. We feed x is equal to 1 back into the original function. That'll give us 1 and a y value. And then we feed x is equal to 3, and that will give us another turning point. So at x is equal to 1, feed 1 in here for x. Be careful with your calculators or with your brain, and we get y is equal to 1. So now our turning point is at 1, 1. We do the same now for the other value. When x is 3, feed that into the original function. We get y is minus 3, and this is our other turning point. So this one is a little bit trickier, guys, because you have to kind of use a little bit of logic. And we now know the curve is going to look something. At 1, 1 there's a turning point. I think I have it here. Yeah. But just when I draw it, at 1, 1 there's a turning point, and then at 3 minus 3 there's another turning point. There's 1, there's 3. The only way these can be joined up is if the highest y value, that will always be a maximum. The lower y value will always be a minimum. It's the only way that can work. There's no other way we can join those 2 dots, and the low y value is a maximum and the high y value is a minimum. So the highest y value, that's the biggest value of the 2, that's the max point, and this one is the minimum point. So there's just a proper picture of the curve. Now normally we don't have to draw this, but I'm just showing you where these points are. There's 1, 1. There's 3 minus 3. And I think you can see from this curve that this one is the local maximum and this one is a local minimum. So 1, 1 is the maximum point, and 3 minus 3 is a minimum point. So there's a little bit more intuition required there, but you just take a look at the y values. Whichever one is highest is going to be your maximum value. Now we'll take a look at a simple cubic. Remember, a simple cubic only has one x term. It must be cubed, otherwise it's not a cubic. So there's no x squared bits or x bits or anything like that. And these are the ones, like I said, typically in science, these are the kind of functions we'd be dealing with. First we find dy dx. Then we let dy dx equal to 0. So 3x squared is equal to 0. Divide both sides by 3. We get x squared is equal to 0. And the only thing multiplied by itself, which will give us 0, must be 0. So x is 0. Now we feed this value back into my original equation to get the y value. I know x, I want to find y. So my x looks like this. It's pretty simple when we feed it in. Just let x equal to 0 and we end up with y will be minus 3. And because it's a simple cubic, again, we'll just take a look at the graph now. A simple cubic always gives us this curve. And the turning, there's only one turning point. And like I said, it's like where a maximum and a minimum have joined up. And this kind of idea where it's both kind of a maximum and a minimum, that's called a point of inflection. Now, later on in this lecture, we'll look at a more formal way of determining, again, without having graphs or without having to ask, is it a smiley curve, is it not smiley, is it a polynomial cubic, is it a simple cubic? There's a more mathematically robust way of determining if it's max, min, or point of inflection, and we'll take a look at that next. So that's what we're now going to do, is take a look at what's really going on at a turning point. So as we can see, the max and min of a critical point, it can often be determined just by simple analysis. Like I said, is it a smiley quadratic? Is it a not smiley quadratic? Is it a polynomial cubic? Is it a simple cubic? But we need to know a more secure way, because if we come across a very complex function, which might have several peaks and troughs, now there's no real rules of thumb that can be at play. Because here we have a minimum, but it's higher up than this maximum. So none of our little rules of thumb apply. And in science, we'd often come across quite complex functions. We want to be able to zoom in at any point of interest. And without having to draw the graph, we want to ask ourselves the question, well, is this point a maximum? In other words, have things stopped growing and now they're starting to decay? Or here, at a minimum point, has the value stopped decaying and now is starting to grow again? Because in science, these are obviously critical. And that's where the word critical comes from. They're very important. These turning points are critical phases of a function. So we're going to take a look at a minimum point first, and we're going to look at the slopes. So try and bear with me now. This just takes a little bit of understanding, but if you get your head around it, you'll be rock solid. So we just go back to the function we've been looking at. Here's its curve. But now we're going to take a look at the slopes. So as we go from left to right, here the slope is very steep. The slope is getting it's negative as well. It's very negative. Now, as we move along the curve, the slope is still negative, but it's getting less and less negative. At the turning point, the slope is 0. And then the slope starts to increase. It's positive and gets more and more positive as our x values get bigger. So as we go from left to right, we start off with a very negative slope. Then it kind of goes to being 0. And then the slope starts to increase. So this is just a little diagram of our slopes. So what we can say is we're going from negative to positive as we roll around this curve. We can say at a minimum point, the rate of change of tangent slopes is increasing as we go from left to right. Now rate of change is got by dy dx, and tangent slope is also dy dx. So we're essentially multiplying these. We're getting the derivative of a derivative. So the rate of change, that's d dx, that's just, normally we would have a y in here, but we're not done yet, of tangent slopes. So we're getting the derivative, this is a derivative, and we're getting the derivative of that. So the rate of change of tangent slopes is negative. So first of all, we just do the maths on this. These are multiplied. Top by top, we get d squared y over dx squared. And that's called the second derivative. But the rate of change of tangent slopes is positive. We're going from negative to positive, so they're increasing as we roll around the curve. So essentially, at a minimum point, the second derivative is positive. So d2y dx squared is also called f double dash x. And as I've been saying, it's the second derivative. So all these things mean the exact same. It just means you differentiate twice. At a minimum point, the second derivative, the rate of change of tangent slopes, is going from negative to positive, so it's increasing. The rate of change is positive. So for our example, the first derivative we've seen is 2x plus 2, but now we just differentiate again. So exact same rules. When we differentiate 2x, we get 2. And that's our second derivative. And we can see it's plus 2. So the 2 actually doesn't matter. The 2 isn't giving us any information, but the plus is what we're looking for. The second derivative is positive. Therefore, we can say we're dealing with a minimum point. As the second derivative is positive, this confirms our turning point is a minimum point. So we don't need any analysis. We don't need to go, oh, it's a smiley curve. Now that always helps, but this is kind of the definitive acid test. What does the second derivative say? If your second derivative is positive, we're dealing with a minimum point, and then as we'll see on the next slide, if the second derivative is negative, we're dealing with a maximum point. So we look at a maximum point now. So here I've just changed the sign on the x squared, so we're now not smiley kind of curve, a maximum point. And if we look at the slopes, the slope here is very positive. Getting less positive, the slope is 0. And now the slope starts to go downhill and get more and more negative. So we start with positive and we end up with negative. So our rate of change of tangent slopes is decreasing as we roll around a maximum curve, because we start, remember, positive slope, it's uphill from left to right, and here the slope is downhill. So we're going from a positive slope to a negative slope. So our slopes, our rate of change of slopes, is decreasing at a max point. And again, when we put it into formal language, the rate of change, ddx, of tangent slopes, dy dx, we multiply those out, and it's negative. Starts positive and then decreases down to negative. So if you think of your bank balance, if you started off with lots of money and then ended up with very little money, you'd obviously say the rate of change, my rate of spending is, well, my rate of bank balance is decreasing. Your rate of spending is probably increasing. So the rate of change of tangent slope at a maximum is negative. So our second derivative is negative for a maximum slope. I hope I'm not confusing you now. We'll have a little table in shortly that'll sum up everything. So at a max point, second derivative is negative for our example that we were looking at. There's my first derivative, and when I differentiate again, I'll end up with minus 2. And like I said, I'm not so interested in the 2. I'm interested in the sign. The second derivative is negative. And that tells us then we're dealing with a maximum point. So for a point of inflection, well, we've looked, a maximum point is if the second derivative is positive. A maximum point has a second derivative that's negative. A minimum point has a second derivative that's positive. For a point of inflection, well, it's neither positive or negative. The only thing it can be is 0. If the second derivative is equal to 0, that means you're looking at a critical point, which is a point of inflection. So I know it's probably confused in your head now. So this is just a little table that sums up everything we need to know. So for all critical points, first of all, the first derivative must be equal to 0. Remember, that was our definition when I was talking about the bicycle with the spirit level. We're looking for where the slope is 0. So the first derivative is always 0, but then the second derivative is the acid test. At a maximum point, the second derivative is negative. At a minimum point, the second derivative is positive, and at a point of inflection, the second derivative is 0. So we'll just look back at the examples now that we've covered earlier. I'll speed through them a little quicker. This is the first one we looked at. There was our first derivative. We let that equal to 0 and we found our turning point. But now we get the second derivative. We can see this is positive. So that means officially and definitively we're looking at a minimum point. So I don't need any graph. I don't need any kind of interpretive analysis. My second derivative tells me definitively it's not the 2, it's the positive. It's a positive value. As the second derivative is positive, it could be concluded that this turning point is a minimum. The next example we looked at was this one. There's our first derivative. We use that first derivative. We let it equal to 0. We solved for x. We fed the x value into the original function. We found our turning point. And now we just differentiate again. And we'll end up with minus 4. 0 minus 4. It's the minus that counts. Because its second derivative is negative, we're dealing with a maximum point. So we don't need to sketch smiley curves or anything like that. There was this one. It's our first derivative. We found our turning point. And now we look for the second derivative. The second derivative is going to be plus 2. It's positive. Second derivative positive means we're dealing with a minimum point. So this is what I'm saying is like the second derivative is your acid test. That tells you definitively what the nature of your critical point is. Our cubic, we found dy dx, we let it equal to 0, and we got 2 turning points. Now when we get the second derivative, it's neither positive or negative, it's 6x minus 2, but we feed in each x value. So we're interested in when x is equal to 1, feed that into this function. Our answer is minus 6, it's negative, so that means this point is a maximum. We do the same now, we feed 3, the other point, in. When x is equal to 3, we feed that into our second derivative. We get 18 minus 12, which is plus 6. My second derivative is positive, so that means this point is a minimum. So we don't need, remember for the polynomial cubic I was saying, oh, it's the highest y value. That's kind of grand, but it's a very limited form of analysis. This second derivative is absolutely definitive. There's just no questioning or querying its kind of determination. We had the cubic function, the simple cubic. There's my first derivative. From there I solved for x, gave me x is 0. I fed that 0 back into the original equation. I got y was minus 3. Here's my second derivative. Now we can't say this is positive or negative at the moment, guys, because it depends on what x is. But we know we're interested in this turning point when x is 0. My second derivative is 0. So remember, it's neither positive nor negative. When the second derivative is 0, our turning point is a point of inflection. And it's that kind of like a chicane idea, that if you were driving a car and you were looking at, you were here the steering wheel, you're always turning the steering wheel to the right. At this moment, the steering wheel would be level before we started to turn the steering wheel back to the left. So that's a point of inflection. Second derivative is 0. So there's our answer. So this kind of just definitively, you work your way through the system to find the turning point. We've done that in the earlier part of the lecture. And then you confirm the nature of the point using the second derivative. So now, here's a question for you guys to try. Find the turning point of this function. So just pause the video and you've seen me working through the process. Here's another one then. Polynomial cubic. But again, guys, you should be using the second derivative to determine the nature of each point. Here's just another one. Again, it's a polynomial cubic. And just one more then. And it's a simple cubic. So give those a go, guys. I've already worked through the process, so try and just follow the steps and you should be okay. And that finishes us up for this lecture, finding the turning points of a function using differentiation. So thanks for listening, guys, and sure we will chat to you again shortly.